In this video, we're going to do some ray diagrams for plane mirrors. So we're going to start off with doing a ray diagram for a dot in front of a plane mirror. And then we're going to try to describe the image characteristics. It's going to be a bit hard to do that because it's just a dot, so describing HI versus HO is kind of weird. How do you measure the height of a dot? But we'll do our best. So I'm going to show you the steps involved here. The first thing you want to do is you're going to need a protractor and a pencil, and here's your plane mirror. You're going to draw a ray that goes from the dot, which is your object, to the mirror. And the first ray I usually draw, doesn't really matter where it is, but I usually draw one that's 90 degrees to the mirror. So that way it's right along the normal and it reflects back on itself. So I did my incident ray first, 90 degrees to the mirror, measuring that with a protractor. It reflects back on itself. And then I'm gonna extend the reflected ray behind the mirror. Just extend it far back. As much space as you have, just extend it far back. And I mean, a little trick is, if this is 10 centimeters away from the mirror, you could extend this 10 centimeters behind the mirror. But just extend it far back as dotted lines, because what you've just done here is you've drawn what's called the trace back ray. Now, to find the image, to find where the dot is, you need to actually have two trace back rays that will intersect. So that means that we're going to go back to the dot and we're going to draw another set of rays. So I'm going to draw one, doesn't really matter where it goes. I'll draw one that goes up here. Then I'm going to draw the normal, 90 degrees to the mirror. And I'm going to measure this angle of incidence. And whatever that angle is, I'm going to draw the reflected ray according to the law of reflection. So it's going to have the same angle as the angle of incidence. So, same angle here. Okay? And then, because this is my reflected ray, I'm going to draw the trace back ray as an extension of the reflected ray, all the way behind. And notice that here, where those trace back rays intersect, that is where the image is. That's where the dot is going to end up. And so, it's hard to tell the orientation, but if this was the top of the dot, the top of the object up here, this is still the top of the object, the image here. So it's upright. In terms of type, it's behind the mirror. It's made by virtual traceback rays, so we call that a virtual image. If you had to measure the height here and here with a ruler, again, hard to do with a dot, it would be the same height, HI is HO. And then the DO versus DI, well, if this was 10 centimeters, this would be 10 as well. So you take your ruler, you aim it here, the zero part here at the dot, and then you measure how far it is from here, from the mirror, and that would be your DO. And then for your DI, take the ruler, go from the same point, and then measure to your mirror, and that should be your DI. So they should be the same. There might be a little bit of error when you're drawing, but they shouldn't be too far off. They should be essentially on the right path. Most of the time when there's error is because the angles are not measured properly. So be careful with your angle measurements. So let's recap that one more time. This is the ray diagram for an object, and we want to find its image on the other side of the mirror. The object is simple right now. It's simply one dot. So the first step is draw a incident ray that is perpendicular to the mirror, so 90 degrees to the mirror. That way it's right along the normal, so the ray reflects back on itself. Then you make the trace back ray to go behind the mirror, but you need two trace back rays to make an image, so make another light ray somewhere else. It could go up this way, it could go down this way. It doesn't really matter where it goes. Every light ray you make in this problem is going to intersect at the same spot with the other ones. So we chose to go this way. Make your normal, measure your angle of incidence, use that to draw your reflected ray with the same angle of reflection, extend the reflected ray behind the mirror until it reaches the other trace back ray there, and that's where your image is going to be. Again, you could have drawn a ray here instead, and then your normal, and then measured the angles, and then a reflected ray, and it would still met up at the same spot. So you need at least two trace back rays to find the image over here. And that is a simple example of a plane mirror ray diagram. In your notes, you can copy this out, and you can try the other examples, like this one here, this one here. Now we're going to try something similar, but with a few more steps. Rather than find where the image of a dot is, we're going to find where the image of an actual object is that's more than a dot. We're going to try a pencil or an arrow. So here we have an arrow. It could be a pencil where this is the eraser, that's a pencil top, doesn't really matter. You're going to need your protractor and a sharp pencil. We want to find where the image is on the other side. So we have a lot more than a dot here. If you think about this object has dots all over the place. There's dot, dot, dot. It's basically all dots. So what you're going to do is you're going to choose 2 points on your object that are significant. 2 points that you can connect to make your object. So that could be the top point and the bottom point. And you're simply going to do the same thing we did with the dot, except twice. Once for the top point, once for the bottom point. So let's start with the top point. We'll call that point A, and the bottom point will be point B. We'll make a ray that goes from the top of the object to the mirror. The first ray I'll do is one that's 90 degrees to the mirror, so it's right along the normal. It bounces back on itself. Then we'll do a ray from that same point that's going somewhere else. Doesn't really matter where. It can go up here, go down here, doesn't matter. I chose to go up here because we're going to have to do the same process for B, so I don't want to make it too messy. I want to keep A kind of far away from B. So I do that, I trace the normal, I measure this angle with the protractor, and then I make the reflected ray with the same angle. Then I'm going to trace my traceback rays. So this one, I trace all the way back there. This one I trace back here because they are extensions of the reflected rays. So there and there. And that is your point A that you found. That's point AI. I call that AI because it's A image, and this is point AO for A object. Now we're going to do the same thing, but for point B. So I'll do a ray that goes perpendicular to the mirror, so 90 degrees, right on a normal. It bounces back on itself. And I'll trace the trace back. Then I'll do another ray from point B somewhere else in the mirror. It can go here, it could go down here, it could go up there if you wanted to, but you don't want to do that because you're going to cross through the lines here, and that's going to be messy. So I'll do one that goes down there. I draw the normal. I measure the angle of incidence. I draw the reflected ray based on the angle of incidence, and then I do my trace back. And it's going to intersect there. Don't get confused. Don't say, oh, the point's here because it intersects there. That's a trace back from the point A. You want to focus on the trace backs from point B specifically. You're kind of ignoring A at this point. So this is where B is going to be. And now you've found A and B, and you can connect the dots. A was the arrowhead, so that stays as the arrowhead, and B was the base of the arrow, so that stays as the base of the arrow. And so now you found your image, and you can describe it. So when you're describing it, you can measure. You can see, you can do the location, so DO would be from here to the mirror. So you can try measuring that with a ruler. And then DI would be from the image to here, so you can measure that with a ruler. And what you'll notice is that they should be the same. If this is 10, then that's 10. Orientation, notice that this arrow points up. This arrow also points up. The head of the arrow is still up. So we have it as upright. Size, you'd measure this from bottom to top. So if this is 2 centimeters, that would be your HO. And you'd measure this. If that's 2 centimeters, that would be your HI. And you should see that they are roughly the same unless you had a significant amount of error in your angles. So here it's a little bit off. The angle should probably be a bit larger here. And then we can look at the type. So notice that the image is made by traceback rays behind the mirror. So we would call this a virtual image. So we'll recap that one more time to make sure you understand all the steps, and then you'll try some on your own. So sometimes you'll have an object that's more than a dot, like an arrow, for example, or a pencil, or a flashlight, doesn't matter. When that happens, you choose 2 significant points. If there's more than 2 points, like if you have a triangle, choose 3 significant points. And you're going to do basically 2 rays per point to find the image on the other side. So we'll call this point A, call this point B, so we can keep track. We'll start with 1 point at a time. We'll do point A, we'll do a ray that goes from the point A to the mirror, 90 degrees. It's on the normal, so you draw the reflected ray right on the incident ray. Then we'll choose another area to do a ray. So up there is fine. You could have done down here too. It doesn't matter. We'll do a normal, measure the angle of incidence, and then do the reflected ray according to the angle of reflection and law of reflection. And we'll make our traceback rays the extensions of the reflected rays. That's where point A is. Then we'll do the same thing for point B, 90 degrees, back on itself, make the traceback, then choose any other angle to do for B. So we'll go down here so we don't confuse up here. We'll make a normal, measure the angle of incidence, use that to figure out the angle of reflection according to law of reflection, make your reflected ray, make your traceback, and this is where point B is. This is the top of your arrow, this is the bottom, so you can simply make an arrow. Don't forget to make your image. A lot of students actually get to this point and they forget to connect the dots to make their image after. And so again, after that, you can describe your image using lost or salt, which we did already. So this is an example of drawing a ray diagram for an object that's more than simply a dot. You can do some practice with this one, this one, this one, this one. Those are all in your notes. One important thing to keep track of is when you do this one, you'll notice that the arrowhead is still pointing down. And a lot of students will say that that's inverted because the arrow looks upside down. It's always how it compares to the object. So if the object is pointing down and the image is still pointing down, well, that image is still considered upright compared to the object. So keep that in mind as you do these problems. So what we're going to do now is we're going to take a look at why is it we think there's an image behind the mirror. And we've already seen this when discussing ray diagrams, but essentially what happens is incident rays from the object hit the mirror, they bounce off the mirror and go into your eyes. Your eyes don't realize that this reflection component is happening. They don't even realize that there's a mirror there. You know there's a mirror there, but your brain can't biologically perceive that. So it thinks that the light rays are coming from behind the mirror and essentially just extends those reflected rays behind the mirror and thinks it's a full ray. And so that's why you see the image appearing behind the mirror as opposed to in front of the mirror. This problem here, identifying where the viewer can see the image and what portion of the mirror is required to see the image, that's an extension. So if you want to do some extra practice and you think you really understand ray diagrams well, you're more than welcome to try this extension problem out here. Before we move on to applications, I do want to mention that plane mirrors do actually invert images, but not top to bottom. So that's how we say the image is upright. Instead, the type of inversion is called a lateral inversion. It's a front to back inversion, almost like a left to right inversion, we would say. So you might notice if you ever look at an ambulance when you're not in the car, ambulance is actually spelled inverted like this, which is kind of weird. And think about it when you look at an ambulance when you're in the car. So let's say you're in the passenger seat, or if you're, if you're sitting in the front in the passenger seat, and you see an ambulance behind you without turning your head, you're looking into a mirror, and then you see the word ambulance written properly. So that's because it's spelled inverted here, laterally inverted, and then a mirror, it flips it left to right, so you can actually read it properly as the word ambulance. But again, it's not a top to bottom inversion. That's why we say that the image is always upright, but there is a lateral inversion that happens. And we don't really describe that in the lost or salt situation. Lastly, we have applications of plane mirrors. Plane mirrors are used for a variety of different things. We have them used in bathroom mirrors, and they're useful there because you see what you are, essentially. So you see your height, your size, your distance from the mirror. It doesn't distort things. You look the way you look there. There are some, of course, minor differences in terms of your tone of your skin and all that based on how the mirror is made, but very useful for that. Small personal mirrors are often plane mirrors. There's a cool little toy called a periscope. You might have seen those before, where you hide behind some object and you can still see everything in front of that object because you have, let's say, a plane mirror here that gathers light from it, reflects it to this plane mirror, and that goes into your eyes. Dental hygienists, some of their mirrors are plane mirrors that they put into your mouth so they can get the same size. Some cameras have plane mirrors in them to basically gather light from the outside and then reflected into the viewer's eyes. So you can see a plane mirror over here like that. So there's proper angles being reflected over here to go into your eyes. And then they can also be used to take selfies. Back in the day, we used to take selfies in front of plane mirrors. So this is an actual camera, and this is one of your fellow Thomas A. Blakelock teachers taking a selfie when they were very young in front of a plane mirror. So to summarize your notes, you're recommended to make an example of plane mirror ray diagrams in your notes and describe what salt or lost means with a focus on plane mirror diagrams. So focus on how would you describe the characteristics of images using a lost or salt, and please make sure to complete practice problems and worksheets provided to you, as you'll only understand this concept in optics with repetition. With practice, you'll get better and better and better. You'll start off slow when you're doing your problems, but then eventually you'll speed up as you become used to the steps, and you sort of memorize but also understand the steps as you repeat them over and over and over again.